Hello, hi, welcome back to EDUHUNT, IIT and NEET foundation classes. This is Sukumar, your chemistry mentor. See, in the previous class, I explained valence shell electron pair repulsion theory. See, basically that theory is to determine the geometry of the molecule or bond angles or shapes of the any molecule or ion. Suppose you are having a formula in front of you, formula of a molecule, formula of ion, you are having a formula in front of you. Now you must be in a position, as a chemistry student, you must be in a position to propose structure to that formula. Okay? For that what we need? We need a theory that is called valence shell electron pair repulsion theory. That theory was proposed by whom? I explained in the previous class. Proposed by whom? Sidgwick and Powell. First they proposed and later developed by two persons called Nyholm and Gillespie. Why, sir? Why? What they proposed and what they developed? See, initially Sidgwick and Powell said that there is certain number of electron pairs around the central atom. Simply I am saying, see, every molecule has central atom. Central atom has valence shell. Valence shell has electron pairs. Depending upon the number of electron pairs, you can determine the geometry. So simply, the number of pairs, the number of electron pairs around the central atom is going to determine the geometry. How? Simply, Sidgwick and Powell practically they determined that if there is 2 electron pairs, the geometry is linear. 3 electron pairs, geometry is trigonal planar. And 4 electron pairs, tetrahedral, 5 electron pairs, trigonal, bipyramidal, like that. See? But the point is, that theory is not enough. That theory proposed by Sidgwick and Powell is not enough, because the electron pairs around the central atom, all pairs are not bond pairs. There are 2 types of pairs. Some are bond pairs and lone pairs. Then we need to update the theory. That job was done by Nyholm and Gillespie. See, all these concepts I explained in the previous video theoretically, but now I am going to explain the same points with an example, with a particular example. Okay, take pen and notes, write down the running notes. Okay, whatever point I teach, write down the running notes, and don't hesitate to reach us if you got any doubt in the class. Okay, yes. But before that, I hope you remember there are 2 things, like there is the point like molecular geometry and electron geometry. First thing, electron geometry. Electron geometry. And the second thing called molecular geometry. Molecular geometry. Okay? Both are not same. Electron geometry is different from molecular geometry. Sir, what's the difference, sir? See, simple. See, if there is a central atom and there is let us say 3 electron pairs. Okay? And according to Sidgwick, if there is 3 pairs, then the electron geometry is trigonal planar. What Sidgwick and Powell said, if there is 3 electron pairs, the arrangement of the 3 pairs will be trigonal planar. This is electron geometry. But while we propose this electron geometry, we don't bother about whether the 3 pairs are bond pairs or lone pairs. We don't bother. This is electron geometry. We are going to represent both lone pair electrons and bond pair electrons, all pairs same, no differentiation. But when you have to determine the molecular geometry, you need to be particular about which pair is lone pair and which pair is bond pair. Let me tell you this. See, this is, for suppose among these 3 pairs, among these 3 pairs around the central atom, let us suppose 2 pairs are bond pairs and 1 only lone pair. Then what happens? One bond pair with a bond to the side atom, another bond pair, and this is only lone pair. Now this is called molecular geometry. This is called molecular geometry. So while we consider molecular geometry, you are not going to. So molecular geometry otherwise called shape of the molecule. Molecular geometry otherwise called shape of the molecule. So when you have to determine the shape, don't consider this lone pair. Don't consider this lone pair. Now how it is looking like? It is looking like a bent molecule, na? Bent molecule. So that's the difference. So while determine the electron geometry, you take all lone pairs and bond pairs, totally you determine. Okay. So along with lone pairs and bond pairs, all electron pairs together looking like trigonal planar. All electron pairs together looking like, together gives, all electron pairs together gives trigonal planar. But here among these electron pairs, one lone pair, so you have to neglect that. That means you have to neglect it and you consider only bond pairs. Then what is the geometry given by these 2 bond pairs? Angular or bent molecule. So that's the difference you have to keep in mind. Okay. Yes. Now try to take one by one example to understand the concept better. See, I hope you are looking this. See, first of all we are taking this AB2 type. Sir, what I mean by AB2 type? AB2 type means the central atom is A and there is 2 side atoms. There is 2 side atoms, and what is this 2, sir? This 2 is to give total electron pairs. So see, this is for electron pairs and this is for bond pairs and this is for lone pairs. Okay. So what this data is telling you, around this central atom there is 2 electron pairs, but the 2 electron pairs are bond pairs only, no lone pair. Okay. Then simply according to Sidgwick, what happens? There is 2 electron pairs. Whenever there is 2 electron pairs, the electron geometry is going to be linear. Electron geometry is going to be linear, but these 2 electron pairs are considered to be what? Bond pairs only. Then electron geometry and molecular geometry, that means both are going to be linear. So shape is also linear. Bond angle 180 degrees. Linear. Okay. I hope you understand. And one more thing, if you want, you can determine the hybridization. How? To determine the hybridization of the central atom, you need to calculate the steric number. How? In the previous class, I explained that hybridization concept. How to calculate the steric number? Number of sigma bonds. How many sigma bonds? 2 sigma bonds. And number of lone pairs. There is no lone pair. Lone pair number is 0, na? Yes, 0. So 2. So when the steric number is 2, that hybridization is SP. You know how to do it. So SP hybridization, linear. And for few examples I have given here, BeF2, beryllium difluoride, beryllium dichloride and mercury chloride also. Okay, I hope you understand that. Let's move on to the next example. Now I have taken 2 here. First of all, let's discuss this AB3 type. AB3 type, AB3. What is AB3? This is the A is the central atom. A is the central atom. 3 side atoms, okay. And 3 electron pairs, but all the 3 are bond pairs. Okay. See, what is the case here is, when you take central atom with 3 electron pairs, whenever there is 3 electron pairs, the suggested electron geometry by Sidgwick and Powell is trigonal planar. Trigonal planar. Now the 2 cases comes. The one case is if all are bond pairs. If all are bond pairs, that means there is 3 electron pairs, all are bond pairs, no lone pair. Then make these electron pairs as a bond pairs. Then A, B, B, B. Now what do you understand? The electron geometry is trigonal planar. The electron geometry is trigonal planar. And molecular geometry, that means shape also trigonal planar. shape also trigonal planar. Now let us understand, what if among these three pairs, what if one pair is lone pair and other two pairs are bond pairs? If one pair is lone pair, then how to determine this? That means you have to leave this pair, right? Then it will be like A with one bond pair, another bond pair, and you leave this lone pair. So for this only the formula given like this. How? A, B2, and this lone pair is represented with the E letter. Okay? And I have told you that if there is a 3 electron pairs, trigonal planar is the electron geometry, but molecular geometry. In what way molecular geometry otherwise called? Shape. The shape is angular or bent molecule. Angular or bent molecule. I hope you got to see bent molecule, angular or V shape also you can say. Examples are here, SnCl2, PbCl2, right? Trigonal planar. See, the point is you can determine the hybridization. See, in both cases I have given sp2 hybridization. How? sp2 hybridization now determine the steric number. S is equal to number of sigma. How many sigma you are able to see here? 3 sigma. And is there any lone pair? No, na. So 3 plus 0, 3. When the steric number is coming to be 3, then the hybridization will be sp2. Okay, let's do that for this also. Steric number is equal to number of sigma, sigma, sigma. When there is single bond, sigma. Double bond, 1 sigma. Triple bond, 1 sigma. Okay, yes. See, I told you several times, when there is single bond, sigma only. Double bond, 1 sigma, 1 pi bond. When there is triple bond, 1 sigma, 2 pi bonds. Among these 3 bonds, if one bond is sigma, other 2 can be pi. Okay, yes, so fine. How to calculate S value? Sigma, sigma, 2 sigma and one lone pair. One lone pair is there. So anyhow the value will be 3. Na? So again sp2 hybridization, that's the data. So this is how we have to determine the bond angles or like that. So see, if you want you can determine some point regarding bond angle also. See, in the theory part I explained you, lone pair repulsion is more than, that means the repulsion between two lone pairs is going to be more than the repulsion between lone pair and bond pair. Then in that case what happens? Here all are bond pairs. So a bond pair repulsion is going to decide this bond angle. Na? But here see, let us suppose this is theta 1 is the bond angle. Here the theta 2 is the bond angle. But the point is, I tell you that theta 1 is going to be greater than theta 2. That means this bond angle is going to be less. Why? Here this bond pairs, these two bond pairs are repelled by bond pair only. But here this lone pair is repelling the bond pair. So obviously a lone pair causes more repulsion than bond pair. So that's why because of this more repulsion, this bond angle is going to be less. That kind of guess you can, right? You can have that kind of guess, right? Regarding the structures, or you are not supposed to by heart all the bond angle values. You have to guess which bond angle is going to be less or which bond angle going to be more comparatively by applying the concept given in Vesper theory. Okay, let's move on. Similarly, here I have taken another kind of concept. That means, what is the concept here? Another kind of example or case you can say. What is the concept or what is the case when there is 4 electron pairs around the central atom? Now I am going to apply the Vesper theory when there is 4 electron pairs. Simply Sidgwick and Powell said that when there is 4 electron pairs, the electron geometry which gives minimum repulsion is tetrahedral. So you have to arrange the 4 electron pairs tetrahedrally. That's it. I hope you are able to identify tetrahedral electron geometry in my diagram. Okay, is this looking like tetrahedral? Yes, yes. There is a central atom. Around this central atom there is 4 electron pairs. Now Sidgwick and Powell don't bother about whether these 4 pairs are bond pairs or lone pair. They simply look at the electron pairs. Whenever there is 4 pairs, tetrahedral. Tetrahedral. tetrahedral is the electron geometry. Electron geometry. But okay, and what is going to be the hybridization? 4 electron pairs, 4 pairs, whether they can be lone pairs or bond pair, 4. When you get the steric number 4, the hybridization going to be sp3. Okay, now what is the case? Among this, what if one pair is, what if one lone pair? Among these 4 pairs, what happens if there is one lone pair? Let us say this is the one lone pair and rest of the one lone pair and rest of the 3, and rest of the 3 are bond pairs. No problem. Then A, this is A, central atom A, then B, B, B. Among these 4 pairs, I have taken one lone pair. Okay. Now, what is the molecular geometry or shape? Shape is going to be, don't consider this pair, then shape is going to be pyramidal. Shape is going to be pyramidal with 3 corners. You can say trigonal pyramidal, trigonal pyramid. This is the formula we are representing like AB3, AB3, and this lone pair represented E. Okay. For this, if anyone asks what is the electron geometry, then 1, 2, 3, 4, consider all of them and say tetrahedral. Electron geometry is tetrahedral, but molecular geometry is pyramidal. When you have to say molecular geometry, don't consider lone pair. What is molecular geometry? Molecular geometry means shape. When you have to determine shape, ignore that lone pair part. Okay, that's what given here. A, B, 3, 4 pairs. Yes, 4 pairs are present. But among these 4 pairs, 3 are bond pairs. Bond pair, bond pair, bond pair. 1 is lone pair. But again I am telling you, steric number is going to be S is equal to 3 sigma, 3 plus 1 lone pair, 1, 4. When steric number is 4, hybridization is going to be sp3 only, na? Yes, but the shape given is trigonal pyramidal. What examples you get in this? Ammonia, and NH3, PH3, PX3, etc. Yes. Now what? If there is 2 lone pairs, if 2 lone pairs, what I am telling you, among these 4 electron pairs in this tetrahedral electron geometry, what happens if the 2 of them are lone pairs and 2 only bond pairs? Then simply take the tetrahedral electron geometry, but consider one lone pair, another lone pair. See, you can draw these lone pairs in anywhere. Okay, first draw the electron geometry. Among these 4 pairs, you take any 2 pairs as bond pairs, any two as lone pairs. So this is B, B. Then what is the formula going to be here? A, B2, E2. The 2 lone pairs are represented as capital letter E. The electron pair, lone pair represented with the capital letter E. Okay. So the electron geometry tetrahedral only, but the bond angle is going to be, shape is going to be. When you have to determine the shape, don't consider the lone pair. Then this is looking like bent molecule, angular, bent molecule, V shape, V shape. This is going to be V shape, or sometimes it is called angular or bent molecule, bent molecule. Okay. Examples H2O, SCl2, OF2, like this. I hope you understand this. See, if you don't attended that previous class in which I explained the theoretical part of this Vesper theory, please watch that video, then come to this video. So there I explained all the theory parts. Now I am applying that theory part to these particular examples. Okay? Yes. Now what is this case? Same. AB5 means I am taking what happens, how to determine the geometry when there is 5 electron pairs around central atom, when there is 5 electron pairs. Yes, Sidgwick and Powell said that when there is 5 pairs, all the 5 pairs will orient in space in such a way to have minimum repulsion. How? When there is 5 pairs, the electron geometry is trigonal bipyramidal, trigonal bipyramidal. How it looks like? A trigonal part, trigonal, triangular part, trigonal, one pyramid like this, one pyramid. So trigonal bipyramidal. See, what I am telling you, for these are the 5 pairs, but we don't know. See, one line, I am representing one line as a one pair here, okay. I don't know among these 5 pairs, all are bond pairs, some are lone pairs, some are bond pairs, I don't know. 5 pairs. When there is 5 pairs, according to Sidgwick and Powell, trigonal bipyramidal. Now the question, what happens? What if one lone pair? What if there is one lone pair? See, here the point is, among these 5 positions, all the 5 positions in trigonal bipyramidal are not same. All the 5 positions in trigonal bipyramidal are not same. These 3 are called equatorial positions, and these 2 are axial positions. See, whenever there is lone pairs, the lone pair must be present at equatorial position. So, simply saying, lone pair prefers equatorial position. Why, sir? Why? Because in the theoretical part I explained, because in the equatorial orbital, the hybrid orbital present, what is the hybridization? sp3d. But the hybridization in the equatorial portion is going to be sp2, this is sp2 orbital, this is also sp2, 3 sp2, and this axial is going to be pd. Okay, I explained how it is going to be like this in the theoretical video while explaining hybridization. Now, what is simply you can observe here is, in the equatorial orbitals there is S character. Please notice here, in the equatorial orbitals there is S character. More S character means more electronegativity, or you can say more S character means more tendency to grab electrons or electron pairs. So, that is why whenever there is a lone pair prefers first equatorial positions. Okay? Yes. Now, come to this part. What happens when there is one lone pair? First of all, when among these 5 pairs, if there is only one lone pair, give that one lone pair one of the equatorial position. Yes, lone pair. Rest of all bond pairs are like this, AB. So, the electron geometry is same, trigonal bipyramidal, trigonal bipyramidal. Here also electron geometry trigonal bipyramidal. But what about shape? What about molecular geometry? Now, ignore this. When you ignore this, this is going to be seesaw. The kids will play in the garden like this, seesaw, right? One kid will be here, one kid will be here. If this kid goes down, this kid will be moving to upwards like that, right? Yes. Seesaw shape, seesaw. And the examples are SF4, SCl6. Okay. Now, next case. What happens? What happens if there is 2 lone pairs? Simply, I told you already, whatever is the lone pairs first prefers equatorial positions. Now, central atom A, one equatorial given lone pair, another equatorial. I am giving these 2 equatorial. See, all the 3 equatorials are same. And again, bond pair. One bond pair to the side atom B. See, what is the formula for this? AB4 and 1. See, AB5 actually. See, one in the place of one bond pair, you are taking one lone pair, right? AB4E. Now, this is going to be AB3E2. Now, this is T shape. It is looking like this, na? T shape. Okay, T shape. But all are having same hybridization. I hope you understand. How? 4 sigma, 1 lone pair, total 5, sp3d. 4 sigma, all are same. 3 sigma, 2 pairs. Steric number, how to determine steric number? S is equal to 3 sigma, 3 plus 2 lone pairs. So, number of sigma plus lone pairs gives the steric number. If steric number is 5, sp3d. If steric number is 5, sp3d. Now the last case for this 5 electron pair model, what happens if there is a 2, if there is a 3? What happens if 3 lone pairs? Among the 5 electron pairs, if all the 3 are lone pairs, then I told you several times, if there is lone pairs, they prefer what? They prefer equatorial positions. Then one equatorial occupied by lone pair, another equatorial occupied by lone pair, third equatorial also occupied by the third lone pair. The 3 pairs. Now this is the axial position occupied by bond pair, axial bond pair. See, so electron geometry is trigonal bipyramidal, but the molecular geometry shape is going to be linear, A, B, 2. Don't look at the lone pairs while determining the shape. Linear. All are having same hybridization. How? 2 sigma, 3 lone pair. Total steric number is going to be 5. sp3 dehybridization. Look at the examples. And apply the concept to the real examples. Okay, try to apply the concept to the real example. I have explained how to determine the structure for XeF2, structure for I3 minus, structure for ICl2 minus. Okay, in the previous videos also theoretically I explained, and while explaining the hybridization concept also I have given some examples. Okay, apply the concept, try to determine the geometry and molecular for this particular example. See XeF2. Simply XeF2, simply Xe, xenon. How many valence electrons in xenon? Xenon is a 0 group element, right? 8 valence electrons. Okay, fine. 1, 2, 3, 4, 5, 6, 7, 8. And I hope you know halogen can form only single bond here. Yes. So then 1f. Now determine how many electron pairs? 1, 2, 3, 3 lone pairs, 2 bond pairs. 3 lone pairs, 2 bond pairs. The electron geometry is going to be same, trigonal bipyramidal, but the shape is going to be linear, XeF2 linear. Okay, are you able to understand or not? Yes. If you have some doubts, don't hesitate to reach us. Do message. Next, same concept. Yes. Now what happens if there is a 6? What happens if there is 6 electron pairs around the central atom? See, when there is a 6 electron pairs around the central atom, this is the central atom, 1 electron pair, another electron pair, another electron pair, another. Try to understand this as a square planar part. Above the plane, 1 electron pair, another below the plane, and one electron pair. How many electron pairs total? Whether they can be lone pairs or bond pairs, there are 6. Whenever there is 6 steric number is 6. The geometry is going to be, the electron geometry is going to be octahedral. And there is a 6 bonds sp3d2 hybridization. Steric number is going to be 6 na. Then sp3d2. Now the question arises, what happens if there is one lone pair? Now see, it may look like different, but the point is, it is not like that trigonal bipyramidal. In trigonal bipyramidal geometry, there is different kinds of positions. 3 are equatorial and 2 are axial. But in this octahedral geometry, all positions are same. All positions are same type. There is nothing like equatorial and axial. Okay, all positions are same. So then, what to do? Give this lone pair to one of the positions. See A. For better look, I will give the lone pair below, and now how it is looking like? A, B, B, B. So among the 6 pairs, 1 pair is lone pair. Rest of the 5 are bond pairs. Now, what is the geometry you are going to observe here? This is a square pyramid. Okay, hybridization is same, sp3d2, square pyramidal shape. Look at the examples. Apply the concept to the examples. Okay, now what happens? What happens if there is 2 lone pairs? In this 6 electron pairs, what happens if there is 2 lone pairs? Now simple, very simple. Central atom A, I am giving 1 lone pair above, 1 lone pair below. Okay, and rest of the 4 are bond pairs, A, B, AB, AB, AB. Electron geometry is octahedral only. Electron geometry is octahedral only. But molecular geometry, shape is going to be square planar. This part is just like, this is square planar part, this square planar part. Okay, square planar. Okay, apply the concept to the XeF4, XeF4 xenon. What is the number of valence electrons in xenon? 8 valence electrons, right? 8 valence. 1, 2, 3, 4, 5, 6, 7, 8. One fluorine. I hope you know fluorine forms single bond. Another fluorine, another fluorine, another fluorine, and this lone pair. Yes, right? Yes. So electron geometry is octahedral, but the shape is, don't consider these lone pairs, then the shape is square planar. I hope you understand this. Okay? Yes. AB7. Now what's this case? What's this case? It's nothing but when there is 7 electron pairs around the central atom. See, when there is 7 electron pairs around the central atom, the geometry is going to be pentagonal bipyramidal. Pentagonal. First write the pentagonal part. How? Pentagonal part. This is pentagonal. See, maybe you are looking this on board like this. Actually, this is like this. Bipyramidal. See, one pyramid to the top and like this, bipyramidal. Okay, pentagonal bipyramidal. Now, okay, so what is the steric number? S is equal to total how many? Total 1, 2, 3, 4, 5, 6, 7. 7 pairs. The pairs can be bond pairs or lone pairs. 7 pairs. When the steric number is 7, the hybridization is going to be sp3 d3. 7 sp3 d3. Now the question arises. There is 7 electron pairs, all are bond pairs, no lone pairs. That is the case. Pentagonal bipyramidal. IF7 is the example. Now what happens? What happens if there is one lone pair? This is the example in our syllabus. Okay, one lone pair. What happens? If there is one lone pair, you have to give that lone pair to this one of the position of the one of these positions, like C. What happens? A, let us say I am giving lone pair here. That means one lone pair here and rest is like this. B, 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 B. See, it is just looking like octahedral, na? It is just looking like the square planar part, above the plane one bond, below the plane one bond, just previously we discussed octahedral. But this is not that exact octahedral because of the repulsion caused by this lone pair present in between. So that's why this is called distorted octahedral. That means the regular octahedral, the bond angle is somewhat distorted, somewhat moved from the original angle. Okay? Yes. So I hope you understand this Vesper theory. Let's meet in the next class. Thank you.